What we have here is a hydrocarbon. Okay, it's made of carbons and hydrogens. It's a hydrocarbon, and we have oxygen. So this must be a combustion reaction. We haven't predicted the products yet. It will when we get there. Okay? So the classification is a combustion reaction. Okay?
What if, like, for the answer they put silver nitrate, nitroxide plus something? I don't know. Does that count for anything?
Doesn't sound like it. Okay? Alright, so we're going to have, anytime you have a combustion reaction where you have a hydrocarbon fuel and oxygen, this is what you're asking about, Todd. You're always going to have CO2 and H2O as the products. Okay, well that's what we're going to do next. Okay? So there's really not any balancing formulas here. There's really not any, the predicting of the products here is really super simple for combustion reactions. Once you identify it as a combustion reaction by the hydrocarbon fuel and the oxygen, predicting the products is super simple. Okay, all you have to do is put down CO2 and water. Okay, and now we're ready to do an atom inventory to balance the overall equation. So let's put down CHO, and there's our sneeze. Okay, I see 4 carbons, 10 hydrogens, 2 oxygens. I see 1 carbon here, 2 excuse me?
When it's 2, does it mean something? When it's 2, like a 2?
Well, I'm just saying that's the joke is there's our sneeze. See, just CHO, okay? I'm using that as a verbal device to try and help you remember that's what you're writing down here, okay? And we're going to have 3 oxygens, 2 here, plus the 1 oxygen here, okay? So I'm going to save oxygen for last, and we're going to save hydrogen for next to last. We always save oxygen for last and hydrogen for next to last, okay? So I have 4 carbons on the left. To get 4 carbons on the right, I need to, remember I can't change the subscripts. I can only change the coefficients. So I'm going to put a 4 out in front, and that's going to give me 4 carbons, but it's going to change the number of oxygens. So I'm going to go over and do a little math. 4 times 2 oxygens is 8, plus the 1 oxygen gives me 9 oxygens. So I'm going to change this to 9. So the carbons are balanced. Oxygen has to be saved for last. We're ready to balance the hydrogens. I've got 10 on the left and 2 on the right. I can't change subscripts. I can only change coefficients. So I could put a 5 here. Good. So that'll give me 10 hydrogens, and it's going to change the oxygens again. So 4 times 2 is 8. 5 times 1 is 5. That gives me 13 oxygens at the moment. Okay? 4 times 2 oxygens is 8 oxygens. Plus 5 times 1 is 5. And 8 plus 5 is 13. And I put the 13. There were originally, but now I just changed it when I put this 5 here. You have to recount the whole thing. Okay? Yep. No. No. What we did was we had 9 a moment ago. When we put a 5 here, we didn't add 5. We added 4 more. Okay? All right. Now we have that situation. Please give me your attention. Now we have that situation where we've got an even number of oxygens on one side and an odd number on the other. So what we want to do is to go through the equation and multiply all the coefficients by 2 except for the coefficient that's in front of oxygen. Now, you know there's a 1 that's implied here. So when I say multiply by 2, I mean multiply the implied 1 by 2, which means we simply put a 2 here. This gets marked out and we put an 8 here. This gets marked out and we put a 10 here. So now I have to go back and recount everything. So 2 times 4 carbons gives me 8. 2 times 10 hydrogens gives me 20. The oxygens don't change. On the other side, 8 times 1 carbons is 8. The oxygens are 8 times 2. That's 16. 8 times 2 is 16. Plus, so I'll put a plus here. And I need to, 10 times 1, or 10 plus 10 oxygens is 26. Okay? So we're going to change this to 26. I'm going to go over here and say, what do I need? What coefficient do I need to change this 2 oxygens into 26? And the answer is 13. Yeah, this will be double replacement. And here's how you know. This is an ionic compound. You know that because there's a polyatomic ion in it. Okay? If there are more than 2 elements, and a bunch of, and it doesn't include carbon especially, because sometimes you can have organic compounds with more than 2, but more than 2 elements, and you're going to look on the common ions list and see if you can find a polyatomic ion that looks like it. And trying to find there's hydroxide right there. Okay, so sure enough, there's a polyatomic ion just like what's in there. All right, and so that's one way to tell when you have a ionic compound. We know it's ionic because of that. We know this one's ionic because we have a metal bonded with a nonmetal. Okay, a metal bonded with a nonmetal. We know it's that because on the periodic table, there's that big stair step running across the back side, and aluminum is on the left side, chlorine is on the right side. So that makes everything on the right-hand side is a nonmetal, chlorine is a nonmetal, everything on the left side is a metal. Okay, and so this would be an ionic compound. So it's got to be two-part compounds. And if you want to, you can call this A, B, C, and D, where A has to join up with D. Okay, now let me back up real quick to our single replacement. All right, with single replacement reactions, figuring out if you have a driving force was all about the reactants. If the reactant, the element that's by itself, is higher on the activity series than the reactant that it's like in the compound, or the element that's like in the compound, then you have a driving force. But for double replacement reactions, we have to figure out the products before we can figure out this driving force. So for double replacement reactions, the driving force is all about the products. Okay? So we're going to have to do this first. So we're going to put Na with Cl, and then we're going to put the front part of this with the back part of that. C goes with B. So Al and OH. Now I'm not going to balance the formulas yet. I want to find out if I have a driving force first, because if I don't have a driving force, I don't have to do anything else. So we need to look at the solubility rules. Okay, now notice we have water around, so anything that is soluble on our solubility rules will be dissolved in water. Anything that's not soluble on the solubility rules will be solid. We don't have water here. That's one of our driving forces, the formation of water. We don't have anything forming a gas, so we don't have either one of those driving forces. The only driving force we have available is the formation of a solid. So if I look at NaCl, I'll look at the first solubility rule and see that group 1 salts. Well, sodium is in group 1. It's in the first column of the periodic table. So we know that's soluble. It also has chlorides listed down here as soluble, and there's no exception for anything in group 1, so we know this is soluble. Since there is water, we can see the aqueous on the other side of the equation. We know this is also going to be aqueous. Okay? Remember, the solubility rules tells you what can happen. You have to figure out if it will happen, if it will be aqueous. All right, let's look at hydroxides. Aluminum is not listed anywhere in here, but hydroxide is. Here's hydroxide. All hydroxides are insoluble, except group 1, strontium and barium. Well, aluminum is not in group 1. It's certainly not strontium or barium, so there's no exception for this particular compound. This hydroxide must be insoluble. So even in the presence of water, it will be a solid. So we do have a driving force, and this reaction will proceed. Now we have to balance this formula. So we look on the periodic table with oxidation numbers. And aluminum is right here, and it has a 3+ charge. So aluminum has a 3+ charge. And we go to the common ions list, and hydroxide is going to have a 1 negative charge. A 1 negative charge. Okay? All right? So we're going to have a 3+ here, and we're adding that to a 1 negative. And when you know what coefficients we can put into this equation to give us a 0 overall. Yes, it's going to be a 1 and a 3. Well, it isn't always. That you have to be careful about that. Okay?
That's the first thing.
But an awful lot of the time it is. Okay? So we know we're going to need one of these, and we don't have to write coefficients of 1. We're going to have 3 of these. So then what we need then are 3 hydroxides. And to show 3 hydroxides, if I just do that, that looks like I have 3 hydrogens. I want 3 hydroxides. So I put a parentheses around the whole thing to show I have 3 hydroxides. Okay? All right. So this is a double replacement reaction. Okay. And we now have, we predicted the products correctly. Okay. We balanced the products correctly. So now we're ready to balance the overall equation. We use the atom inventory chart, put down our elements: sodium, oxygen, hydrogen, aluminum, and chlorine. And we make our little spreadsheet or grid chart. We want to try to put this line directly under the arrow just to kind of keep up with what's on the left and right. And we count everything. We have 1 sodium, 1 oxygen, 1 hydrogen, 1 aluminum, and 3 chlorines. Okay, over here we have 1 sodium. Let's go ahead and put our 1 chlorine down here. I didn't show you how to balance that. Do I need to go through that one? Okay. Sodium is 1 plus and chlorine is 1 negative. Okay, it works the same way as this, and it's a lot simpler, but most of you are familiar enough with sodium chloride now to know. All right, so over here, this 3 outside the parentheses means everything inside gets multiplied by 3. So that means we're going to have 3 oxygens and 3 hydrogens. And then there's just 1 aluminum. There's no subscript after the aluminum, there's just 1. All right, so we're going to save oxygen for last, hydrogen for next to last. That's always the way we do it. And we're going to start with chlorine then. Since I have 3 on the left, I need 3 on the right. So I'm going to put a 3 coefficient. Remember, this formula is already balanced. I can't touch it. Got to leave it alone. I can only use coefficients to balance the equation. That's going to change the number of sodiums to 3 and the number of chlorines to 3. Okay, well now we can't balance oxygen and hydrogen yet because we've unbalanced the number of sodiums. So to fix this, we've got to put a coefficient of 3 in front of this. That will give us 3 sodiums, and this 3 multiplies everything inside. Since there's 1 oxygen currently, we're going to have 3 of those. The 3 also applies to the hydrogen, and that took care of it. Everything is balanced now.